Hello there and welcome to this video. Well, in this video we are going to prove that the integer part of the square root of n plus the square root of n plus 1 is equal to the integer part of the square root of 4n plus 2, where n denotes a natural number. Now, before we get to the proof, I would like to make some observations that will help us during the proof. Now, the first observation by those red brackets, so I mean the integer part of a real number. Some people use this notation and refer to it as the floor function, but the floor function of a real number or the integer part of a real number is the same. But I prefer to use this notation, the integer part. Moving on now to observation number 2. By n star, I mean the set of all natural numbers where 0 is not included. So all natural numbers except 0 defines the n star. Moving on to observation 3. So since n is a natural number, then both numbers, namely the square root of n plus square root of n plus 1 and the square root of 4n plus 2, are positive real numbers. Now, in the next observation, I would like to compare those two numbers. So by squaring the square root of n plus the square root of n plus 1, so by squaring this sum, so I will get the square root of the first term, which is n, plus the square root of the second term, which is n plus 1, plus 2 times the first one times the second one. And if I multiply those square roots together, I will get this expression. Now, by distributing n into n plus 1, so I will get the next expression, 2n plus 1 plus 2 square root n2 plus n. And by moving now 2 under the square root, I will get the following. Now, moreover, since 4n squared plus 4n is strictly less than 4n squared plus 4n plus 1, it follows that the square root of 4n squared plus 4n is also strictly less than the square root of 4n squared plus 4n plus 1, which means that the whole 2n plus 1 plus the square root of 4n squared plus 4n would be strictly less than 2n plus 1 plus the square root of 4n squared plus 4n plus 1. Now, why do we do this? Well, this is because the number under the square root here is a square itself. So this is equal to 2n plus 1 plus the square root of 2n plus 1 squared, which gives us, of course, 2n plus 1 plus 2n plus 1, which gives us 4n plus 2. So we have shown here that the square root of n plus square root of n plus 1 is strictly less than 4n plus 2, but this means that the square root of n plus the square root of n plus 1 is strictly smaller than square root of 4n plus 2. So that was observation 4. Now, moving on, observation number 5. If p is a natural number, and if we divide p by 4, then we can have 4 different remainders, namely 0, 1, 2, and 3. Which means that by squaring any natural number, the remainders upon division by 4 would be 0 and 1. So thus, p square is congruent to 0 mod 4, or p square is congruent to 1 modulo 4, where p is a natural number. So those were my 5 observations. And now, before to start with the proof, I would like to make a plot of the proof. So I would like to see how I am thinking here, and then we will start with the proof. So what I do here is I will choose an arbitrary natural number p. So p is any natural number different from 0, such that p is strictly greater than the square root of m plus the square root of m plus 1. Now, by showing that the same p is strictly greater than the square root of 4n plus 2, so by doing this, we can conclude that there can be no natural number that lies between this number and that number. So, I repeat, so I start with a natural number which is bigger, strictly greater than this number, and I would like to come to the conclusion that the same p here is strictly greater than this number. So by doing this, we can conclude that there can be no natural number that lies between these two numbers, and thus they have to have the same integer part. So this is the plot of the proof. Now to the proof itself. So I start with a natural number different from 0, such that this natural number p is strictly greater than the square root of n plus the square root of n plus 1. In the next step, I raise to the power 2 both sides of the inequality. So I get p square is greater than, strictly greater than, the square of this number, which means that p square is strictly greater than, now we've done this before, and we will get this one. In the next step, I move the 2m plus 1 term to the left, so we get p square minus 2m plus 1 is strictly greater than the square root of 4n squared plus 4n. And now I square both sides of the inequality once again. So I will get p square minus 2n plus 1 altogether squared, strictly greater than 4n squared plus 4n. Now notice that both sides of the inequality are natural number, which means that if this one is strictly greater than this natural number, then this one, the same one as above, is strictly greater or equal to 4n squared plus 4n plus 1, which is the next natural number after that one. Now, why we do this? Well, you can see here that then we get p squared minus 2m plus 1 altogether squared will be greater than or equal to 2m plus 1 squared. And now, by taking the square root of both sides of the inequality, so we get this one. And by moving, once again, 2m plus 1 back to the right, so we get p squared is greater than or equal to 4n plus 2. Now, to complete the proof, we need to do one last thing. We need to show that we can rule out we want to rule out the equality sign here, so that we only have p squared strictly greater than 4n plus 2. So I repeat, we want to rule out the equality sign in this inequality or this expression. But remember from the observation number 5 that we showed that the square of a natural number is congruent either to 0 mod 4 or 1 mod 4, while for n plus 2, this one, for n plus 2, is always congruent to 2 mod 4. What does this mean? This means that p square and 4n plus 2 can never be equal, and therefore we can rule out the sign, the equality sign, and therefore we have left p square is strictly greater than 4n plus 2, which finally gives p is strictly greater than the square root of 4n plus 2, and we are done. So this is the proof. So to sum up what we've done, so we started with an arbitrary natural number different from 0 by assuming that it is strictly greater than the square root of n plus square root of n plus 1, and we came to the conclusion that p is strictly greater than the square root of 4n plus 2. But this means that there does not exist any natural number such that this natural number lies between those two numbers. So this means that the integer part of square root of n plus square root of n plus 1 is equal to the integer part of square root of 4n plus 2. Now, I'm not going to stop here. I'm going to go a step further here and show you the following. So I want to show you that the integer part of the square root of 4n plus 1 is equal to the integer part of the square root of 4n plus 2. And this is the proof. So we let the integer part of the square root of 4n plus 2 be equal to p, where p is a natural number different from 0, and by definition of the integer part function, or by definition of the floor function, this means that p is less than or equal to the square root of 4n plus 2 and strictly less than p plus 1. And by squaring, we get p squared is less than or equal than 4n plus 2, strictly less than p plus 1 squared. But we know that from before that p squared can never be equal to 4n plus 2. So we get this double inequality, p squared strictly less than 4n plus 2, strictly less p plus 1 to the square. But we know that this is even strictly less than p plus 1 to the square plus 1. And you're going to see soon why I add plus 1 here. So this means that, since every term in this double inequality is a natural number, so then I can say that p squared plus 1, the next natural number after p squared, is less than or equal 4n plus 2, strictly less than p plus 1 squared plus 1. And now, by subtracting 1 from every term of this inequality, so we get p squared less than or equal 4n plus 1, strictly less than p plus 1 squared, which mean by taking the square roots now, that p is less than or equal the square root of 4n plus 1 and strictly less than p plus 1, which is the definition of the integer part of the square root of 4n plus 1. So thus, we have proven that those two are equal. And we can go even further here and prove that those two are even equal. So finally, we have proven this wonderful, beautiful equality. Cool, huh? So please comment on this and tell me if you like it or not. And by the way, I have another proof. I have even another proof to this integer part function that I will take in the next video. Thank you and bye-bye.